Hey! If you're diving into data science, there's one algorithm you absolutely have to know. Linear regression. It's the bread and butter for predicting continuous values, and honestly, it's one of the simplest ways to start making sense of real-world data. Imagine you're trying to predict house prices based on square footage, number of bedrooms, maybe even the neighborhood. What linear regression does is draw the best-fitting straight line through all your data points. Like, literally the line that hugs your scatter plot the closest. This line is basically your prediction tool. You feed it your features, and out pops a predicted value. At its heart, linear regression is built on an equation you might remember from algebra, y equals mx plus b. But in machine learning, we jazz it up a bit. Y equals w1 times x1 plus w2 times x2, all the way to wn times xn plus b. Here, vi is your prediction, say, the price of the house. The x's are your features, like square footage or bedrooms. The w's? Those are the weights or coefficients. They tell you how much each feature actually matters. For example, if W1 is huge, it means square footage really impacts the price. And B is your bias or intercept, what the prediction is when all features are zero. So how does the algorithm find the best weights and bias? It uses something called ordinary least squares, or OLS. All that means is it tries to minimize the sum of the squared errors between its predictions and the actual values you have. Imagine drawing the line so that, overall, it's as close as possible to all the points on your scatter plot. But here's the catch. For linear regression to actually work well, there are a few important assumptions you have to check. First, linearity. There needs to be a straight line relationship between your features and the output. If the data curves or zigzags, linear regression just won't cut it. Second, no multicollinearity. Your features shouldn't be super similar to each other. If two features are almost the same, the model gets confused about which one matters more. Third, normally distributed errors. The differences between what you predict and what actually happens should look like a bell curve, not something lopsided or wild. Now, linear regression is powerful, but it does come with limitations. It's super sensitive to outliers, those wild data points way off in left field. Just one or two of them can pull your best fit line totally out of whack. It also can't handle non-linear relationships. If your data doesn't follow a straight path, linear regression will miss the mark. And finally, it assumes each feature is independent, which isn't always true in real life. Bottom line, linear regression is an awesome starting point for data science. It's simple, interpretable, and surprisingly effective if your data fits its assumptions. But always be aware of the scenarios where it falls short. Mastering linear regression gives you a solid foundation for understanding more complex models down the road. So, next time you see a straight line slicing through a cloud of dots, you'll know exactly what's going on underneath. Happy modeling!